Hello, it's Keith here, and this is lesson 1 of the multi-platform series of my 6809 assembly programming tutorials. The multi-platform series is where we write little code snippets that you could use in your own games if you wish. Basically, these only really rely on things that the processor can do itself, so they should be portable to different systems. So we're looking today at our example code is going to be running on the Vectrex, but the routines we're looking at you could just copy over to a Dragon or any of the 6809 system, and they should work fine as well. So that's why we refer to this as the multi-platform series, not like the platform-specific series where we're looking at things that only work on a certain kind of hardware. Now, today, for a bit of fun, I thought we'd start trying to make a very simple version of... I made a game called Suck Hunt, which was a rail shooter, a bit like Operation Wolf or Duck Hunt, on the Amstrad CPC and a few of the Z80-based systems. And today we're going to be making a very simplified version, or starting to make a very simplified version, on the Vectrex called Suck Shoot. Now, the concept of the game is going to be sort of similar. We're going to have a bat on the screen, and we're going to have to shoot that bat. So today we're going to start looking at that, and we're going to look at two functions which I think will be very useful, possibly, if you're just getting started, because these are copies of some functions I wrote in the past that I've used on a lot of different games. One is a random number generator, which we can use to generate pseudo-random numbers, and we're going to use this to position the bat on the screen today, the X and Y position of the bat. The other one is a range checker, and what this does is it takes a coordinate and a range and a second coordinate, and it checks if the first coordinate is within the range of the second coordinate. And so this is used for collision detection, basically. In this case, we're going to hide the bat when the cursor goes over it. You can see that happening in the animated GIF over there, but eventually we'll use it for checking if the player has shot the bat or whether the player's missed, and you would use this in other games. My YQuest game on the other systems, Z80, and that lot, it used it for checking if the player had hit an enemy and died. And so this is something you're going to need in a lot of cases, and I've got a routine that you can look at today. Now, both routines today, I can't say the best, I'm sure they're not, but they work, and they are compatible and functionally identical to the other ones I've written in the past. So I try and make games that I can port to other systems quickly and easily, and so my random number generator will work in the same way on all the systems, and it will actually produce the same random numbers given the same random seed on all the different CPU types. So that's really the benefit of it, plus the fact that this random number generator has been used on about 3 or 4 games now, and I've not come across any serious problems with it. So hopefully it's reliable. So as I say, not saying anything I'm doing today is the best in the world. It definitely isn't. It's just usable if you need a solution. Here is one that you can use, and you're welcome to. Let's go over to the source code. Let's see it running and have a play with it. So here is our code today. So we're not really going to go over the code that is actually the Vectrex stuff, because this is a multi-platform episode, so not the purpose of it today. So here's our Vectrex emulator, and if I move the joystick, you can see we're moving our cursor here. Now, the game as it stands at the moment, we can't shoot the bat, but what we can do is we can test the collision detection. If we move the cursor over the bat will temporarily disappear. So that's what's happening when the collision has been detected. So later on we'll put a shoot routine in there, but that's not there yet. So that's one thing we can do. The other thing is if we press fire, we will re-randomize the bat position. So you can see that's the random number generator in action, and again we can just use that to check our collision detection is working correctly. So that's really all we've got at this stage. So there we go. Now, what have we actually got in our code? Well, first of all, let's take a look at the random number generator. Now, the random number generator is designed to produce a 16-bit result from a 16-bit random seed. Now, the game we're using here actually only uses 8-bit values, 8-bit random numbers, but we combine the two 16-bit parts. So that's something you'll see later on. This was originally written for a game called Chibi Aliens, and it was being used to produce predictable random numbers for the purpose of world generation. So, let's say you had Planet 1. Planet 1 would have certain things in it, and they would be in the same position every time on Planet 1, but rather than having a huge table of planets, you use a random number generator from a predictable random seed, and you get the same result every time. That's why it was designed like that. So it's just a bit of background there. So we've got a random seed variable here in memory. This is the random number generation seed, and we will increment this to give truly random numbers if we want want predictable ones, we just give it the same seed every time we want the same result, that is. Now, the random number generator uses two lookup tables, two 16-byte lookup tables, and these need to be aligned to a 16-byte boundary, so the bottom 4 bits of the address will be 0 for the lookup to work in the way I've written it. So that's something we've got there. Now, the rest of the code is in this random function here, and let's just take a look at it now. So basically we've got two versions here. We've got the do random function, which is for producing an 8-bit number, and what this basically does is it takes the random seed each time, increments it and stores it back, and then it uses the random word function and it combines the two random words together. So this is basically creating a constantly changing random number because we're constantly changing the seed, and it's creating a single byte value, and this is what I tend to use for most of my programs because usually I just want an 8-bit random number. So that's the easiest way of getting that. Now, the do random word function itself uses two different random number generators, one for the low byte and one for the high byte. The reason we have two is because the random seed in the Chibi Aliens game I was writing would only go up by 1 each time in some cases, but we needed both bytes to radically change in the 16-bit value, and we needed them to change in a very different way. There needed to be no pattern between them, otherwise it wouldn't provide the functions that I required. So we've used two very different ways of generating random numbers here. Now, the first way is fairly simple. So this is the first random byte routine, and what we're basically doing is we're taking our 2 bytes of our random seed, C and B here, and we're basically shifting the bits of them around, EORing, XORing them together, XORing in another random value here just to make things a bit more inconsistent, just for if B and C are both 0, for example. So yeah, basically we've got a bit of randomness going on here, and this is a fairly typical one. This is kind of similar to the one in the ZX Spectrum, I believe, so that will produce some fairly random looking results. The problem was that doing the same thing again for the high byte wouldn't really work, because then you would have two that would look almost the same. Even if you use different rotations and things, there would be a very noticeable pattern in the 2 bytes when you compared them. So for the second one, I've done something very different, and what I've done is I'm now using the random seed again, obviously, but this time I'm using these as part of a lookup, and I'm using 2 random lookup tables, the ones you saw before, here to produce values, and then combining those together. And I'm even using the first random number generator to get one of the lookup values, and this produced reasonably random results for my testing. Now, the thing you need to do to make sure your random generator is going to be usable is it needs to create every valid result within the range you're using. So if you're creating an 8-bit random number generator, it needs to create values from 0 to 255. If it doesn't, you might find your game will lock up in some scenario, like maybe you're running it in some weird scenario where only a value of 254 will be acceptable. You know, you've got a range where the new enemy needs to appear or something, and it happens to be only 254 in one case. If the random number generator never produces that number, your game might lock up waiting for it to happen. It never will. So that's a serious problem that you need to avoid. So it's something to test for. And the other thing is, ideally, obviously, you need your random number generator to produce results that don't have any patterns in them. So if you write a program to plot pixels on the screen, it needs to look fairly random, and pseudo-random number generators, especially simple ones, it probably never will be. But the closer you can get to that randomness, the better. So as I say, I think this one's acceptable for my needs at least, and I've not had any problems with it so far. So that's our random number generator, and you can see here when we are randomizing the position of our enemy, we're using 16-bit values for our X and our Y here, just because that is what we're passing to the Vectrex routines, but we're actually only using random bytes here in the low byte of the 16-bit value. So we're just generating a random position for our enemy here, and that's how we're doing that. Now, that's the random number generation. What about the collision detection? Well, the collision detection routine is pretty simple. If we just go over to my screenshot over here. So basically, here's how we do our collision detection. We've got 2 positions. We've got the object we are trying to see if it has collided, and our object that we're testing. So in the case of this game, this would probably be our player cursor, and this would be our bat enemy. And then we've got a width and a height, which is the hit zone of the target. So in this case, this would be the bat, and the bat is wider than it is tall, so we specify those. And what we're doing is we're checking if the player's crosshair is within that range of the position, and if it is, then we're returning a collision, and if it's not, we're returning no collision, and then again we'll decide what to do accordingly. At the moment it's just hiding the enemy. Now, of course, for this to work, we have to specify the center of the enemy. That's something that's important for this routine. And the other thing to bear in mind for this routine in this case is it does work with unsigned values, and the values on the vectrex are actually signed. So I have corrected them just by adding 128, and that's corrected that for us. So how do we actually do the collision detection? Well, here is the range test routine here, and this is what I'm using to do the collision detection. Well, basically, first of all, we're converting the player position by adding 128 hexadecimal 80 to convert it to an unsigned number, and doing the same for the enemy position here. And then we are storing the enemy position in 0-page entries marked as Z, B, and ZC. And we're marking the player position in ZD and ZE. Now, the reason I use D and BC, these are the variable names of the Z80, the register names. So this is to match the functionality, so it's easier for me to port my games. So that's why they don't have any other meaning. The letters are just letters. So we're specifying a width and a height here. We're specifying a width of 18 and a height of 8, and that's the collision area of the bat. If we wanted to make the game harder, more precise, we could lower that. If we want to make it easier, we could make it higher. Okay, so let's have a look at the theory of what we're going to have to do to check the position and the collision. So if we imagine here that we've got our screen. So here is our screen. And then if you imagine we have our bat. That's our bat, and we have a collision zone around it. And whatever the position of the bat, we're going to have to test the collision zone. So we're going to basically take our center point here, and then we're going to subtract the width of the collision zone, and we're going to test this point here. And then we're going to move back to the center and then add the width of the test zone and test this position here. Now, the problem is going to be that if our bat is at the very edge of the screen, remember, the center point is just here, so that the bat's center point is still on the screen, but the extremity of the collision zone here has gone off the screen. And so if this is 0, well, this is minus 32 or something maybe. So basically, we need to deal with the fact that our collision zone might have gone outside of values, and of course a very low value here will wrap back to a very high value here. And if our player's target was here, well, if we tested this, then it might look like our player had shot the bat when actually it's at the other end of the screen. So that is something we're going to be testing for, and you're going to see that in the code here. Okay, so that's what we're dealing with. So we've got our range in H and L here, and what we're basically going to do is we're going to test the x-axis with a set of rules, and then we're going to do the exact same thing to the y-axis. So let's take a look. So basically what we're doing is we're loading in the horizontal position of the test object here, subtracting the range so that we're now testing that leftmost extremity. And then we're checking if we've gone over the left-hand boundary of the screen, gone below 0 basically. And if we have, we're moving on to the next test, because we can't test this one, because as I say, we would potentially collide with the test object, the other test position if it's at the other end of the screen. If we've got a valid position though, we're comparing to the second object. And if the second object is out of range, then we don't need to do any more tests, because we know that if the object is out of range on this axis, then it doesn't matter if it's in range on the other ones. So we're going to skip over there. If, however, it is within range, we then need to check the other side of this axis. So we add the width twice, effectively moving to the other side, moving from here back to the center to the right-hand side. And then what we're doing here is we are doing the test again. Firstly, checking if we've now gone over the right-hand side of the screen, and then checking if the second object is still within range. If it is, then we know if it's between the two ranges, and so on the x-axis it's potentially in position. But of course, just because it's within the range here doesn't mean that it's within the range on this axis. The target could be all the way down here, so we still need to check the y-axis in this case. And so that is what we're doing. We're then proceeding to do the exact same set of tests on the y-axis here. So that's what we're doing. Now, at the end of this code, if we have got a collision, then we are setting the accumulator to 1. If we've got no collision, we're clearing the accumulator, setting it to 0. Now, as I say, this has been ported from the Z80, 6502 and 68000 and now to the 6809. I ported this from the 6502 version, basically. That was the most similar, I thought, at the time. But I thought it was interesting in this case to have a look at the way that those processors in some ways differ. Now, on the left here, you've got the 6809 version of the code. And on the right here, you've currently got the 68000 version of the code. Now, if you look, obviously these commands are very different because this is a 16-bit processor. But you will notice that the conditions are the same here, where you've got a BCS here and a BCC. In the same place, you've got a BCS and a BCC here. And again here you've got BCS, BCS, and here you've got BCS, BCS. So the conditions are working with the flags in the same way as on the 6809 and the 68000. Now, that may or may not be surprising to you, but if we have a look at the 6502 version here, you've got BCS and BCC here, but you've got the opposite, BCC and BCS here. Now here you've got BCS and BCS on the 6809, but on the 68502 you've got BCS, which matches, but BCC, which is the opposite. Now, you might be confused as to why that is. Well, the answer is quite simple, actually. The compare command is effectively setting the flag like a subtraction command on both processors, but the subtraction command on the 6502 uses the carry flag in the opposite way you might expect. A carry flag set to 0 means that an extra 1 needs to be subtracted, which is the opposite of the way that really most of the processors would use that. Usually a carry of 1 would be a borrow of 1, whereas it's a borrow of 0 on the 6502, I guess, effectively. So that's something you'll need to bear in mind if you're converting code from other systems to the 6502 or converting code from the 6502 to the 6809. Now, my understanding is that the 6809 borrowed a lot of its ideas from the PDP-11. I've heard that said. It seems more like a 68000 to me because it's a big endian processor. But it's just, as I say, it's something to bear in mind. I think really the 6502 is the odd one out on that. But as I say, if you're porting code, the 6502 is a good place to start because it's an 8-bit processor that has a 0 page. But the way the subtraction and also compare, because it's a subtraction command, use the carry might cause you some trouble. So just bear that in mind. Anyway, there we go. That's all we're covering today. Now you can of course go to the website and download the source code for today's example and try it out. And as I say, you can use the source code in anything you want. Take it, make better stuff out of it. Go ahead. You're welcome to do so. I don't care. We may have a look at the Vectrex code later in a platform-specific lesson, but as I say, that's not for covering today. What I am planning to do, though, is to add a little bit more to this. I'm going to add some binary-coded decimal score and just finish it out as something that's a bit playable. So we'll probably have another multi-platform lesson covering adding score counters and things like that. Anyway, I hope you've enjoyed this today. If you have, please like and subscribe. I will quickly show my book. It doesn't cover 6809, but if you're interested in the other processors, it covers 6502, Z80, 8086, 68000 and ARM. I do plan on making a second book which will cover 6809. The book's called Learn Multi-Platform Assembly with Chibi Akamas, and you can get it from Amazon now. If you want to support my content, you can of course also back me on Patreon if you wish. Anyway, I hope you've enjoyed this today. Thanks for watching and goodbye.